Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder if those tiny little numbers in psychology studies actually matter? Today we're diving deep into how we interpret the strength of relationships between different things, and whether we're sometimes chasing ghosts with our stats. This paper is a conversation starter, a friendly challenge to some ideas about interpreting research findings, specifically about these things called correlation coefficients and R-squared values. Think of it like this. Scientists often look to see if two things are connected. For example, does more time spent studying connect with better grades? Or does more exercise connect with feeling happier? To measure how strong these connections are, they use numbers. The big question this paper tackles is how we should understand these numbers, especially the small ones. It is looking at a previous article by Thurn and Ozer and saying, hey, that is a great point about small effects being important. But we think there are two key parts to this that need a closer look. So what is the first big point? It is about two ways of measuring these connections, R and R2. The authors here are saying that one of them, R2, is actually a better way to understand how much one thing influences or is related to another. They argue that the way we mathematically handle R can be misleading. Imagine you have two connections. One has an R of 0.4 and another has an R of 0.8. You might think, wow, 0.8 is double 0.4, so that second connection is twice as strong. But these authors say, nope, it doesn't work like that. R has a weird scale, like an ordered list, where the distance between numbers isn't always the same meaning. You can't just say double the number means double the strength. To make this clearer, think about temperature. If it is 20 degrees Celsius and then it goes up to 40 degrees Celsius, it is not twice as hot in terms of the energy you feel. It is a lot hotter, sure, but not double. R is kind of like that. You need special math tricks, like something called Fisher's Z transformation, to actually compare R values properly or to average them. Now, let's talk about R2. This R2 value, which often comes from squaring, R is much better behaved mathematically. It behaves like measurements on a ruler where the distances mean something consistent. So when you look at the difference between two R2 values, that difference is meaningful. For instance, if one study shows an R2 of 0.09 and another shows 0.25, the jump from 0.09 to 0.25 is a statistically solid chunk more connection. That is why when scientists build complex models with multiple predictors, they talk about change in R2 or delta R2 because those differences are meaningful. They don't talk about change in R because, as we said, the scale of R doesn't let you do that. So squaring R to get R2 isn't just playing with numbers. It is a necessary step to get a number that truly reflects meaningful differences in how much one variable is linked to another. Now, the term variance explained is a bit tricky. It sounds like something is causing something else, like a direct explanation. But in correlation and regression, it is more about how much two things are linked or how well one predicts the other, not necessarily a cause and effect relationship. A more accurate way to think about R2 is that it tells you how much of the uncertainty or wiggle room in one variable can be accounted for by another. So an R2 of 0.20 means that if you use some predictor variable to try and guess the outcome variable, you've cut down the error in your guesses by 20%. It's like saying 20% of the fluctuations in one thing are associated with the fluctuations in another. Even though the label variance explained might be a bit of a mouthful or semantically a bit off, the mathematical power of R2 stands. This brings us to the second major point these authors want to make. They agree with Thurn and Ozer that we shouldn't be so rigid with our effect size rules, and that even small effects can be super important. For example, a tiny change in a medicine dose might have a huge impact on a patient's health, making that small effect incredibly relevant. However, these authors worry that Thurn and Ozer's suggestions might blur the lines between the size of an effect and its importance. They argue that calling a small effect large can be misleading. Imagine a hiring process where a selection test weakly correlates with job performance, say at an R of 0.3. Oh, if we start calling that large, HR managers might think the test is incredibly accurate, but when you look at R2, that 0.30 correlation only explains 0.09 or 9% of the variation in job performance. By calling the 0.30 large, we might ignore the other 91% of what makes someone good at their job, the stuff that is still up for grabs and could be improved through better training, different management, or other factors. They also make a great point. If we start calling moderate correlations large, what do we call the really strong correlations that sometimes pop up, like between different aspects of a personality trait, which can be 0.70 or even higher? This new labeling could make it hard to talk about findings across different fields of science. The critical takeaway here is that the relevance of an effect is different from its numerical size. A small effect can indeed have a huge impact, but it is still numerically small. And we need to be honest about that because it tells us how much uncertainty is still in our models and where there is room for improvement. So, what is the story here? These authors are saying that while it is great to recognize that small research findings can be incredibly important, we need to be careful about how we talk about them. They're advocating for R2 as a more reliable measure of effect size than R, because it behaves better mathematically and gives us a clearer picture of how much variance is accounted for. And they're urging us to distinguish between the numerical size of an effect and its practical importance, warning that calling a small effect largest could lead us to overlook significant room for improvement or understanding. It is a call for clearer communication in science, so we don't get lost in the numbers and truly grasp what the findings mean for us. I think this is really important because so much of our everyday world is influenced by research, from the products we buy to the policies that govern us. Understanding how to interpret these effect sizes, even the seemingly tiny ones, helps us be more critical consumers of information and appreciate the nuances of scientific discovery. It reminds us that just because a connection is small doesn't mean it is insignificant, but it also means we shouldn't overestimate its power, leaving room for more exploration and innovation. What do you all think about the difference between the size of an effect and its relevance? Let us know in the comments below. If you found this helpful, please give it a thumbs up. Subscribe to Rubin's Mind Lab for more breakdowns of fascinating research and hit that notification bell so you don't miss our next video. Thanks for watching, and we'll see you in the next one.